afternoon, this is Schweitz. Let's walk through a little video on how do acids, or we know how acids are made, and we did talk a little bit about this, but let's recap this again here. How bases create hydroxides. So we know again from previous videos that hydroxides are the individual piece that makes something acidic. It doesn't matter how it gets it, but that's important to realize. So okay, so metal hydroxide dissolving. This is one of the most common ways, and it's one of the first real ways that people figured out that hydroxides were basic. So the most common base might be like NaOH. Now this is something that you should recognize as being ionic. And this is a bond right here that is electrostatic in nature or Coulombic in nature, where you have a cation attracting to an anion. And when it dissolves, it produces Na plus ions and OH negative ions. Simple as that. It all of a sudden your beaker's got hydroxide floating around. It's going to be very basic. Alright, so next one is hydrolysis. Now, with an acid version, we showed that the acid, HX, donates to the water. And in this case, that produces H3O plus and X negative. But in this case, hydrolysis, we're going to reverse it around. Let water donate. So, and a lot of times you use like a chemical like just like X negative. There's a couple different versions of this, but plus water, and I'm going to let water donate back to this guy. So really we have a water molecule, and we have a chemical coming up like X negative coming up to it and snaking away one of its H's, forming HX, and then this guy is left over, which is OH negative. Now, part of this thing here, when I was seeing this for the first time, I think, okay, yes, I see I have a base here. That's great. But there's a little bit of a problem here, okay? A little bit of a problem that I just created an acid. And I might say to you, I would say, okay, is this actually acidic? And the answer is no. Okay, how can that not be acidic? Well, it's an acid. Yes, but the only way acids become acidic is by going through a chemical reaction, which is hydrolysis. So in this case, it's not quite an acid yet. So keep that in mind, okay? Alright, so this is going to produce before snapshot, after snapshot, HX and OH negative. Okay? That's the general idea. This is going to be a pretty short video. We've already done some of these already, just trying to stamp it one more time. And so, a couple examples here. Hortonville. In Hortonville, our water is very hard due to abundance of dissolved minerals. This is also causing our water to be slightly basic. Write out the hydrolysis reaction for carbonate. Okay, so this is an interesting one because it happens right around here. We have CO3 minus 2. We live on a limestone bed called the Niagara Escarpment. So this stuff is all over our water. And if I react it with water like this, and this does happen in the ground, which is why sometimes it eats away some of the limestone, which is why we sometimes get some caves. And if you've been around north of Wisconsin, you could possibly investigate and see some pretty cool looking caves. Alright, so here we go. And this is going to donate to this guy. Now there's a couple different versions of this. The first one would just be HCO3 minus 1 plus OH negative. Now if we keep going, and under some conditions we could have this happen, we could have this guy pick up another one, H2, I'm just going to start it over again here, so it would be HCO3 minus 1 plus water would yield H2CO3. Now again, there's certain conditions where it would take, this one's very easy, but again, this one we'd have to do a little bit more work to get this thing to do it. Okay, either way, it's possible. Label the acid-base conjugate pairs. Okay, so I'm just going to get a different color here. Let's just label the conjugates first. This is these are conjugates, and these are conjugates. Yeah, they look just like each other. So this is the donator, so this is my acid, and this is the conjugate base. Remember, it flips from one side to the other side. This is my base, it's accepting, and therefore this is my conjugate acid. That's just how we would label it. Okay. Move to the next one. Alright. When you exert your muscles, they produce acid that burns. When milk spoils, Same acid produces a sour taste. Okay, so, all right, so here we go. Give the structure to the right, given the structure of the right hydrolysis reaction, and this, of course, is lactic acid. Lactic acid. Okay, breaks down in your muscles. It's a constant battle between production of lactic acid and breaking down of lactic acid. Same thing with milk. Bacteria take lactose and produce lactic acid. Alright, so in this case, let's write the hydrolysis equation. Now this is an acid, and right here is the donatable H. We've seen this once before earlier. We had this little thing on here called a carboxylic acid. Either way, in this case we have H. We'll plug for H out front, and that's going to be this H right here. And how we write the rest of it sometimes varies, but it's going to be CH3. Let's do that. CH3. And there's a little carbon here. That little carbon, C, O. Let's go happens to have an OH on here. So let's do OH, and then O right there, like that. Okay, that's one way you could write it. Doesn't make a difference. And then this whole thing, sometimes we might abbreviate this whole thing as just being X. If we want to really just abbreviate, we can, but this is going to produce plus water. Sometimes they leave that off, put plus water on here. And this is going to be to produce the conjugate base, which is going to be CH3OH, okay, COO negative. Okay, took the H off. I rearranged it a little bit, but it's the same thing. Plus H3O plus. Okay. Again, we could just say X equals CH3OH COO negative, and then you can just put an X in there if you wanted to. But that's an interesting little example. So again, this is a conjugate acid. This is my acid, and this is my conjugate base. So this is actually basic. All right. You also note that is milk acidic or is milk basic? Milk is slightly acidic. All right. All right. Please take a moment and write out a few base hydrolysis reactions. Okay, so again, I'm telling you they're bases. Okay, so ammonia, NH3, or is a common example. Okay, so let's run this one out. You might want to pause the video and try it on your own. H2O yields. Okay, this is going to donate NH4 plus and OH negative. All right. H2O yields HF plus OH negative. Alright. So NH3 is a base and undergoes hydrolysis. We saw the reaction in the past. If it forms a reactant-favored equilibrium system. So reactant-favored. We've seen this before as well. Okay, so let's write out the hydrolysis equation and sketch a particle model of the reactant-favored system. Okay. So we got NH3 plus we have H2O yields NH4 plus OH negative. Now again, how we write this out can vary a little bit, but almost all reactant favorites, very reactant favored. So we're going to draw this out. Probably going to do NH3, a whole bunch of these. And as I mentioned in a previous video, that these are, it seems like in nature, trying to mimic nature, things are either very reactant favored or very product favored. Very little in the middle. So if I want to draw out some products, this thing is only barely squeaking over. I could draw one of them, but I wouldn't want to draw two, or my ratio would be pretty far off from what I had originally. Okay, potassium hydroxide is basic and goes to completion. Write out that reaction. Okay, so this is a metal hydroxide. We had one of these examples before. KOH yields K plus OH negative. Now this one goes to completion. So let's draw this one out. Only at this point, all my reactants are gone and only have products. So, all right, K plus OH negative. And how many you draw is just how many you start with. You could draw more if you want. This gets more concentrated. Okay. Very good. So, shows kind of a couple different examples. All right. Vinegar is a common acid. We call it acetic acid. But acetic acetate is also a common base. How are these related? All right, so let's write out the hydrolysis equation for both. Remember, they are conjugates. Remember, acids are proton donors, bases are proton acceptors. Let's label the acid-base conjugate pair. So pause the video for sure. Definitely pause the video here. And try out to write out the two hydrolysis equations. This one is the acid, and this one is a base. So if I drop acetic acid into water, what reaction takes place? Pause the video, write it up. Okay, now again, acetic acid, you will notice in our everyday lives, okay, we use acetic acid for lots of things like canning, and for some really gross people put it on sub sandwiches. Disgusting, by the way. So with that being said, we only use very dilute solutions, like not very much actual acetic acids in there, about 3%. So if you were to actually get your hands on some more concentrated acetic acid, you would never put it on anything food-wise. Smelling it is almost impossible. It's just really concentrated. So anyways, plus water yields, it's going to donate and forms H3O plus C2H3O2 negative. And this guy is the base version. That's this guy. Okay? This guy can, again, it's an equilibrium back and forth. It's battling back and forth between these two. This guy is now trying to battle this way, because this is now a base. How does it do that? Well, it uses this reaction. Plus C2H, back up here a second, H2O yields HC2H3O2 plus OH negative. So this reaction on the bottom here, this guy, is actually represented by this arrow. And this reaction is represented by this arrow. So whenever I have two reactions, they battle back and forth, and they get stuck in somewhere in the middle between the two, and a stalemate occurs. And of course, we call this equilibrium. Okay? Whichever reaction is more vigorous determines the winner. So you always have a winner. One wins out a little bit over the other. THR tips a little bit more one way than the other way. Not fully, it's not completely down. It's somewhere in the middle, like that. So either way, a little bit of stuff coming up in the future maybe. All right, so take a minute, pause it out, and let's write out a couple equations. All right, so we got this guy is Na plus OH negative. We have this guy is K plus OH negative, and this guy is going to be Fe plus 2 OH negatives. Okay, so what really determines how strong a base is? In fact, what is a strong base? Okay, it's just starting to get into this stuff a little bit. A strong base is something that essentially goes to completion. Okay, we define it would be a metal hydroxide. Alright, this is your ionic compound. Where that metal, well, first of all, the thing needs to be, and this is the answer to this question, it's a metal hydroxide that is very soluble. And there aren't that many of them. Okay, so really from the first row of the periodic table, we would grab on to a couple of these guys: lithium, potassium, sodium, potassium. Those are the main three guys right here. They're extremely soluble, and therefore are main really strong guys, meaning they're very soluble, meaning that they dissolve nicely and produce these things in high quantities, would be like NaOH, KOH, maybe lithium hydroxide. Okay, these guys too would work, but they are very rare. In fact, francium, little trivia note, there is only about 30 ounces of francium on Earth at any one given time. It's going through nuclear decay and stuff, so it's not a lot around. So that being said, Yeah, strong bases. That's how we would define a strong base. And that's why it's considered strong. It goes to completion and produces lots of hydroxides. Stop there for now. Thank you.